We are asked to list the following compounds in order of their vapor pressure. And we have water, methane, and fluoromethane here. So this is pretty conceptual, and I'll just talk a little bit about vapor pressure in general. So vapor pressure is due to the amount of gas that's in equilibrium with the liquid and or solid phase of that same component. So you have these intermolecular forces that are attracting these molecules together. And to start vaporizing from a liquid into a vapor phase, you need to have enough energy to overcome those attractive forces to escape into the vapor phase. So therefore, the biggest takeaway is that the weaker bond strengths give us the higher vapor pressure because we are more likely to escape into the vapor phase. The attraction in these molecules are weaker. So I'm going to start by listing out in a chart formation relative bond strengths. And this might be really helpful to go back to. So from strongest to weakest, I'll list them out. So first we have ion-ion bonds. Then we have ion-dipole bonds. The next strongest is hydrogen bonding. Then we have dipole-dipole bonds, dipole-induced dipole, and finally the weakest bond strength is going to be induced dipole. So what I'm going to do is go down this list and see if any of these molecules match these descriptions. So first I have the ion-ion and ion-dipole interactions. Well, none of our molecules exhibit this. So we then move on to hydrogen bonding. And for hydrogen bonding, we do have one of our molecules that exhibits this, and that is water. And just a reminder, hydrogen bonding is when a hydrogen bonds to a very electronegative element, and that will be either oxygen, fluorine, or nitrogen. And it is a bit confusing because we do have this fluoromethane where we have a fluorine and a hydrogen, but these aren't actually bonded together. If you draw out the Lewis structure, the fluorine is bonded to the carbon in this case. So because our water has the strongest bond strength, we are less likely to have a higher vapor pressure. So this is actually going to give us our lowest vapor pressure. And then moving on to dipole-dipole interactions, we have that in both methane and in fluoromethane. And so I'll move down here to write this out. So for dipole-dipole bonds, this is due to electronegativity differences. And we can analyze the electronegativity differences in methane and fluoromethane. And if you take a look at the periodic table and see the electronegativities relative to each other, you'll see that in this case, carbon and fluorine have a much larger difference in electronegativity in our fluoromethane than carbon and hydrogen does in our methane. And that's because fluorine is incredibly electronegative, so it's creating a very strong dipole-dipole interaction. So I will write that here. So we have a stronger interaction. And that's due to the fact that we now have fluorine in this case, where in methane we had 4 hydrogens, now we have 3 hydrogens and 1 fluorine. So because this has the second strongest bond strength, this is going to give us our second lowest vapor pressure, and therefore methane will actually exhibit the highest vapor pressure in this case. So to write this out, we have methane's vapor pressure is greater than the vapor pressure of fluoromethane, which is greater than the vapor pressure of water.